Okay, wow, that link is taking an awfully long time to load.
Even before someone clicks editorial.
Oh no, it is there. Okay, no one clicked.
Yeah, don't do that.
Wait, am I reading correctly that it can have 500,000 test cases in the one thing?
The total sum of them is at most. The total sum of all test cases is at most 100,000.
Yeah, never
Or
mind.
500,000. So you can kind of assume there's just one.
Yeah.
Thought it'd be a good idea to keep my voice on so that I can read the problem, and in case I have to talk while reading it.
Just checking, we can't use paper, right? Or like anything.
Yeah, the idea is to not use paper, just to solve in your head. I guess I can explain the general principle of it now. So the idea is we go through one problem at a time. The first one being the link I just sent. We have some time to think about it on our own, and then Jerry, you might want to mute your mic. All right, anyway, back to that. So yeah, essentially present one problem at a time. The idea is solve without paper. So think about the problem. We'll have a few minutes to think about it independently, then maybe share some ideas. Depending on where we're at, might have some more independent thinking. And then once everyone understands the solution, move on to the next one. Does everyone understand the premise?
Yep.
Yep.
So I guess we'll get started now. I'll just briefly explain the problem for anyone who hasn't read it. You have a tree where each edge has a weight. You want to assign k colors to each node in the tree. You have infinite colors to choose from. However, each color can only be assigned to at most 2 nodes. So you can assign at most k colors to a node and each color to at most 2 nodes. Cool an edge saturated if both endpoints have a color, like the same color in their buckets. Calculate the maximum possible sum of saturated edges in the tree. N up to 5 times 10 to the 5. You can ignore the multiple queries. We're just considering the worst case. Does everyone understand what the question's asking? Or does anyone not understand it?
Yep.
Oh, did you mention?
Yes, I understand.
Wait, is k meant to be less than n?
Yes.
If it's greater than n, it's not you can assume it's less than n, I guess. It doesn't really matter.
Because the constraints kind of confuse me for a bit. So
yeah, so if anyone who missed that,
sometimes like you read the constraints first to figure out what kind of problem it is.
Yeah. So if anyone missed it, the problem is the link that's set in general 5 minutes ago. We'll have, I guess, 5 minutes for everyone to think about it. Again, the idea is not use paper. And then we'll share any ideas we have in 5 minutes. If you have any questions about the problem at any point, you can ask them.
May I mention an idea?
We'll just give a couple more minutes to think about it, then we'll share ideas. Do people want more time, or do they want to share ideas now?
I'm fine for sharing.
All right, I guess
Yeah, sharing, please.
anyone wants to share an idea, just go
The-
ahead. Hopefully it isn't too chaotic. Dylan, you can go, I guess.
The first thing to realize is that if every node needs to be colored with exactly k colors, it's equivalent to coloring up to k colors, because if some node has less than k colors, you can just put in a bunch of random colors to complete it.
Yep.
The second thing to realize is that you're trying to select a set of edges on the tree such that no node contains more than k, so no node has more than k of the edges in that set containing it, and you want to maximize the sum weight of edges in this part.
Yes, that's a useful observation, and that is, I'll just repeat it. We can reduce the problem to, for each node, we essentially pick a subset of its outgoing edges of size at most k, and then an edge weight is added if it's in both of its endpoint subsets, if that makes sense.
I would believe this
What, did I
problem
misunderstand the
would be
problem?
complete if it wasn't on trees, but it's on trees, so it's probably easier.
Yes. What was that, Kwang?
I almost definitely misunderstood the problem.
What's your understanding of it?
I thought it was like you could only select like one edge out of every You could only select one edge out of outgoing from every other node.
I guess that could be a subtask, but no, you can select the most k edges from each node. So I guess, does anyone have any
Oh,
more?
each vertex gets k colors.
Yeah.
Oh,
Oh, may I propose squared? And like we can probably optimize it.
Yeah, sure, go.
Basically, you just root arbitrarily. And like you have your you do tree DP. Like it is at a subtree as the edge from this node to the parent taken already. And in that case, what is the best score you can get?
And then with that DP, what's the
The
recurrence?
recursion, you mean? Like if you
It's
go
sibling, right?
you can go sibling, but I think you can just sort and make n log n. It's like sorting, like you can just math it out.
And
Like-
that's essentially,
Right?
yeah, so do you want to explore that more, or does someone else want to explore that?
I
Like, do you
can
have-
going.
you
I
go.
think I see the process. Basically, you want to choose k or k minus 1. Let's just ignore how many we choose. We choose any number of current child edges to choose, right? We add that DP states. Basically, we have like a baseline score for each subtree, which is like if we have already taken one, there is a certain improvement if we don't take a parent edge, so to speak, right?
Yep.
But we just sort these differences and take the best k.
Yes, that's essentially the full solution. Do people want him or someone else to go over again, or do people understand that?
Yeah, can you go over again, please?
So the DP state is, we're going to arbitrarily root the tree. Let's say root it at node 1, and then consider the DP state on a subtree. The state is what node you're at, so what subtree, and also whether your parent included the parent edge in its bucket, essentially, if that makes sense. So that's a state.
Yeah.
Do people understand the state?
Yeah.
So like, I guess a really
Yes, I
kind of,
understand the DP solution.
yeah, so I guess a really slow exponential recurrence would be to consider, well, there's kind of two cases. Case one is the parent edge is included, in which case your options are like pick k take 1 children and take my parent edge, or I guess you can ignore the parent edge and take k children. So in the case where, let's just say we're picking k children, the k best children, brute force is just like try every combination. That's a bit slow. The observation is for each child, we have two options. Either we put its edge in our bucket or we don't. So then for each edge, for each child, call its baseline score the score of if we don't put it in our bucket, and then like the bonus for including it in our bucket is just like the new DP if we include it. And then we can just take the k most, we put k things in our subset, essentially pick the ones where the difference between including it and not including it is greatest. Does that make sense?
yeah, and you can just
Yep.
either sort it or like put it through a PQ and not bother with it. Does that make sense? What I just said?
Yeah. So I guess,
Like in terms of implementation, you can just like chuck all the stuff in like a PQ and chuck all the children their deltas in like a PQ, and if it's like if the size is too great, then whatever.
yeah. So I guess
Yeah.
we have to get the k largest. We can use a priority queue. We can sort. We can even do it in order n if we use like quick search or something. But that doesn't really matter.
Yeah, but okay. So the weird thing is like, I thought the DP state would be like whether or not you take your parents' edge, Wait. Oh no, it's whether. Oh no, it's whether or not that node has taken its parent edge. Yeah, that makes sense. Just trying to figure out which perspective to look at it from.
Yeah.
There's no
So
right-
I guess, do people understand that, and would they be comfortable implementing it? I guess.
I mean,
So people
to say
I
haven't
understand
spoken
it.
yet. People haven't spoken yet. Do you understand it?
Yeah.
All right. I guess if there's no more questions about this problem, we can move on. To a CompGeom problem, and also an interactive problem.
Lovely. Everyone loves that.
Oh no.
Okay, so here's the problem. There are n points on a 2D plane. You don't know the location of the points. However, you do know that no 3 points are collinear. And you also know that these points form the vertices of some convex polygon. So you have n points in a plane where no 3 points are collinear, and they form the vertices the outside of a convex polygon. You don't know where the points are, but you wish to find an ordering of them which is counterclockwise around the outside of the polygon. You have 2 possible queries you can ask. Query 1 is you give it 3 points, and it tells you the area of the triangle formed by those 3 points. The second query is you give it 3 points, and it tells you the sign of the cross product of so you have points A, B, and C, the vector AB and the vector AC. It tells you the sign of the cross product. For
What
those
do
who
you mean? Like the sign of the angle between them?
Yeah,
You-
it essentially tells you whether point B is clockwise or counterclockwise relative of point B relative to point A, if that makes sense. I can
Right.
send a problem statement as well.
Like, does it tell you like the angle between the vector AB and AC?
It tells you whether that angle is positive or negative.
Oh, so it tells you which way they are orientated.
Exactly.
Yeah,
So you
but
have
I'm not really sure if you can think about that. Like, does it only return a Boolean value?
yes.
So if you combine them both together, then they're the cross product. So like the first one is just the sign, and the second part is just the magnitudes.
If you want to know exactly where each one is, you will need to make at least two. You need to make at least n queries to the. You need to make at least n queries. I think 2n queries to find the area of a triangle thing, because you have 2n degrees of freedom in the points. That's in
Hey, nice
continuous
job.
variables.
Yeah. So in the problem, you can use at most 3n queries. I guess some things to consider are there are constraints on the points. They all must form the vertices of a convex polygon. We don't need to find where they are, just an ordering of them that's counterclockwise. Does
Oh, I
everyone,
see.
does everyone understand the problem? We can ask 3n queries of either type. So total 3n queries. The problem link's also been sent. So does everyone understand what the problem's asking?
Yeah.
I guess we'll think about it. Feel free to think about, I guess, subtasks where you have more queries if you want. But we'll just see any ideas and we'll share them in a couple minutes. I guess, does anyone have any ideas? Especially people who haven't spoken yet?
I think I have some that will be quite.
I can find X components of all the points in wait, hang on.
I think I have a
I
solution.
can find X components of all the points in 2n queries. That's it.
What do you mean by X components? Oh, it's
like if you arbitrarily define a vector as like the X vector, like a unit
Yep.
vector in X, then I can find all the all the resolutes of the other vectors in terms of this vector.
okay.
Might be useless.
Can
I guess you can share it.
Sorry.
Oh,
And what was that,
I
Jun?
guess my solution's incomplete, so mine should go first.
Yeah.
Okay. Thank you.
So, okay,
my
I think I
my,
made
my idea is like this. Like, just to find an edge in the polygon, then you get the area of that edge with every other point. Then observe that the areas are like going up and then going down. And decide for each point you query each other point with that edge, like which direction relative to that edge is that point on. And you will be able to divide into two groups and get your polygon. And I will now explain how you will do each of the 3 steps. So for step 1, you wish to find an edge in the polygon, like 2 adjacent points. What you do is you fix any specific point. You find the most counterclockwise edge relative to that point, to speak. Like, you know how you do your standard and the min of an array. It's basically like doing that. Maintain the most counterclockwise point so far, and use your comparator. If you get a more counterclockwise point, you replace it with that, and in the end, you will get an edge in the polygon, right? I don't know if it's right. Do people think that works?
I thought that when you take the sign of
Oh yeah,
the
I fool. Don't worry, I fool.
I thought when you take the sign of the vector product, you're not telling how large you're only telling if the 2 vectors point in the same direction or the opposite direction.
Yeah, so then I think the idea was use that so you kind of keep the best or like the furthest like I guess to the left so far, and then you kind of check your new point comparing to that, and depending on the sign of the cross product, it's either more left or right, and if it's more left, you update your best one.
Yes, Angus, that's a much better way of saying what I tried.
Yes, but I thought that the sign of the cross product would tell if, doesn't tell which point is more left or more right.
Oh, it does tell.
That's precisely what
point
it does.
I thought the sign of the cross product would tell if the 2 lines are close to each other, they point in the same direction, or they point in the opposite direction.
Well, that's dot product.
Yeah, so
Can I
mistake.
give some
Cross product.
intuition?
I see.
you can give intuition, yeah.
So basically, have you learned magnetism yet?
I've heard of it. It's
like, you know how there's a right-hand slap rule, right?
You have the right-hand rule. So you
Nice.
have
Okay, so put your hand up in the right-hand rule position, right?
Yep, you have the middle finger, the fourth finger, and the thumb.
So basically, notice what happens if you switch the middle and the fourth finger. Then your thumb now points downwards, right?
You switch the middle and the fourth finger.
And like in that case, it's like if you switch the vectors, then the cross product flips sign, right? Is what I'm trying to say.
Oh.
Basically, the one that's like more to your third finger is like the more left one, and that kind of determines, like, which is more left determines like sign of your cross product, to speak.
Oh, my mistake. I was thinking about dot product.
Easy mistake to make, no problem.
By the way, Jun, is your solution actually easy to explain? Because like, go on, it's pretty simple.
And it's pretty easy to explain.
All right, then go ahead.
Right. So suppose now we found our edge, right? That edge, we query every area between another point and that edge, right? So once you have that point and an edge, you basically observe that for every other point, if you scan counterclockwise in the polygon, keeping the edge you found in mind, areas of the points increased, and this is because of the half base times height of the triangle rule, right? Basically, get your sequence. Now, problem now is to split this sequence into two parts, one which is the right and the other which is to the left. To do that, we just run our counterclockwise comparator with the edge you found and every other point to see which is right and which is to the left. Is that something like what you had to do now?
Hold up. I guess I'll explain my alternate solution because it's actually kind of cool. Is that okay?
Yeah, you can go.
All right. So same thing, right? We want to find the clockwise most point using Jun's algorithm thing, right? And wait. Actually, never mind. Go Jun's. Jun's is easy.
I was doing something similar to Jun, except this time I didn't even bother with trying to find two adjacent edges. Essentially, I just picked any edge, whatever. Any two pairs of points, and it doesn't really matter which two pairs. And then you can figure out for each point which side of the two edges is on. Does this make sense? By just using the sign of the cross product.
It's very
Each side of both of them.
It's very smart.
Because if you pick any edge, imagine slicing the polygon with that edge, then you can use the cross product to check which points are on which side of the polygon.
Oh yeah.
And then you've also got the area thing, which you can use on each side. But the last bit I don't know, which I think Junhua finished, was whether that thing was decreasing or increasing. Whether because the thing is you observe that the angle will be that the area, if you go along consecutive, if you just query if you have a fixed edge and you query the third point clockwise or counterclockwise around the polygon, the area of the triangle will increase and then decrease monotonically. Just trying to figure out whether that point is on the monotonically increasing or the monotonically decreasing side is the hard part I'm trying to work out. Did that register for everyone?
That was really good explanation.
Okay.
The way I proposed to do the last part of your solution was to run the comparator, the clockwise comparator, with the signed direction, signed edge, right?
Hmm.
So
Yeah.
consider as a Woolog the counterclockwise direction, and then you run the comparator for every other point and your current edge. And what you're doing in that case is basically see which points are counterclockwise and which points are clockwise. And I believe that it is exactly the counterclockwise points that make up the increasing arc.
So what are you comparing them to, sorry?
It's really hard
Basically,
without a
given-
diagram. It's brute forcing through all the possibilities you could be talking about.
Basic-
Oh, I think I figured something out. When you do your triangle thing, you take the max edge, right? You take the triangle with the max max thing, and you kind of somehow figure out how to split it. Oh, okay. I have a solution that's simple to understand. I have a solution that's simple to understand. The way I'm gonna split it up to the yeah, that's what Jerry has. You find a triangle with the max area, and you do it for both sides, right? you do it for both sides of this cut polygon, and just to say some queries, I believe. And then you can find like clockwise and counterclockwise. The only problem I have with that is like, what happens when the split you choose to begin with is like already adjacent, or just some like nasty edge cases, or how can, because I'm not 100% sure if you can still like you've got like you've got a bunch of split consecutive segments that you've worked out, but I'm not sure how you can work out for sure which order they go in.
I think Jerry's got it. I think his solution.
No,
is
I buy it.
I buy it.
That was the idea I just had.
If you're curious, my solution involved kind of using cross product to like find the resolute of the vector perpendicular to the vector you're querying, which is really hard to explain because like there's a lot of flipping involved, but it eventually allows you to find all of the coordinates of the points in terms of two different vectors. You've like essentially made for yourself a basis, and that basis can't be flipped. Okay, whatever.
Oh,
Interesting.
It's just a cool idea.
I think I've done
How many
that.
queries did yours use?
3 and -1.
Oh wait,
Chinan, how many queries did you use?
3 and -1.
Okay. Yes, I guess the solutions that Jun and Kwang presented are pretty similar. They kind of differ in the first step. And then I guess Jerry clarified the final part. Do people understand that solution in its entirety, or does someone want a specific part of that solution to go over again? I guess Jordan's solution, the first part is find some 2 points that are adjacent on the outside. From there, using area, you can find the distance of each point from that line. You get the maximum one, and as Jerry said, you split stuff to the left and to the right, or counterclockwise and clockwise of the maximum point away from the edge. And then from there, you just sort them by their area, and that gives you your order. Right? Does anyone not understand the solution, or one of the two solutions, or I guess one of the 3 solutions?
awfully quiet.
Yeah. I think next time we'll get some of the people who haven't spoken yet to explain stuff, but I'll put the problem up first. We'll think about it, and then, yes, some of the quiet people can speak. Which one? Which problem to go with? I guess perfect time for Jason to join because we're starting a new problem. Right, I'll go with what I've called on my notes grid problem. So in this problem, you have a 2D grid. You have a number of points, endpoints, all at integer coordinates on the grid, and each point has an associated cost to it. You want to choose a square which sides are parallel to the coordinates, and also which lies on the diagonal y equals x. So a square which has bottom left and top right corners along y equals x and is a square. And then the value of this square is the sum of all the points in the square minus the side length of the square. And the question is, what is the maximum value square you can get in the grid? But
Is that like a subtask of a certain IOI problem?
I mean,
Can confirm it has like
Is it-
one of the.
it's been a while since I've read. Is it actually just a subtask of Alien? If I, no, I can move on.
Oh, it's not a subtask for Alien. I believe the idea is same.
The idea is close to Alien, but whatever.
Is it? Okay. Do you have a solution already?
No, like the question
Yeah,
is
I
idea.
just need
I
to.
mean, the question is similar to an IOI problem, but I didn't actually compare the solution. I will stay with this problem. So bounds are up to 100,000 points, or maybe 500,000 points, Grid size is up to 10 to the 9 by 10 to the 9. The link's been sent. Does anyone have any questions about the question? I think there's a no. I guess we'll have some time to think about it then. And then some of the quiet people can share ideas. I guess, does anyone who hasn't said anything yet got any ideas for this problem? Arthur, Isaiah, James, Jason, Josh, Xavier, Pat, any of you?
Nothing.
Kind of getting sliding window-ish vibes. Sort of weirdly, I don't know, I'm kind of getting panorama vibes. Because you can like slide along the line with your like the corners of your square and kind of do it that way. Or
Yeah. I guess that's something worth noting because you can, I guess, use some way to like slide along the diagonal. I guess, yeah. Do you want to you're talking to the line of ranges. Do you want to share that reduction? So I guess we could use some sort of sliding window, but yeah, feel free to type. Perhaps we could explore that once we have some more ideas such as this reduction. Yeah, so I guess the reduction which was just said is consider each point and the main diagonal. If you draw a vertical line up or down and a horizontal line across and see where they meet the main diagonal, this point will only be included in some square if the entire range lies within the square. I guess we can think about it as we're going to pick some line along the main diagonal, and a point is only included if that line entirely contains the range. So you have a bunch of ranges on a line. You want to pick another range on the line such that sum of ranges contained within the bigger range minus size of range is maximal, which I think is what's being said in the chat. Here's another way to think about it is, you can reflect points. Any point underneath can be reflected across the line as well, because reflection doesn't matter in this case. Do you want to share your sweep idea? I guess you can write it if you want, or talk, whatever you think's easiest.
Okay, fine. I wonder how much faster I can get my thoughts out by just talking. But basically, every right endpoint, you want to find the left endpoint that kind of works the best, right? And well, you can essentially when you sweep over to the right endpoint, when you increment your right endpoint, if you you're basically trying to enumerate through all the possible queries from going from the right to the left. If they're you're trying to enumerate all the possible squares with the left endpoint. Yeah, basically what Tunan said. You're trying to enumerate through all the possible left endpoints given a fixed right endpoint when you're sweeping. And what you can do is when you encounter a range's right endpoint, what you can do is you can be like, oh, hey, from here on out, I will be including this right endpoint will be covering this new range or this new point, and it will add to my total. does this kind of make sense? And essentially, like, you take the left endpoint of that range, and then you update that value of the seg tree. No, you update the values of the prefix leading up to that point, because you add the range, because now every single left endpoint to the left of that left endpoint of the range. Holy crap, this is probably really confusing. It will now include that new range / point that we have just included, right? And to address like the to address the fact that you still need to subtract the side length of the side length of the square, then you can just do a pretty trivial. I say trivial because this has appeared in too many problems, and it's kind of like cheaply increasing the problem difficulty. Where you basically like either add or subtract the index, and yeah, it just works. You do it in a way that works, if you catch my drift.
Do people understand that, or did they want explained again?
Someone didn't understand that.
Because I guess there's a lot there.
Yeah, you need to do like a. You can probably hack around like some kind of lazy seg tree. I'm not sure.
Yeah, it's lazy prop seg tree with coordinate compression.
Yeah,
Yep.
it's kind of cancer. Wait, I money with wings, Italy.
You can probably get away with not coordinate compressing, but it's probably easy if you do.
I mean, if you're feeling extra, you could like lazy create.
Oh, I buy it. Get it? I buy it.
I see. I guess it's kind of harder to deal with the size condition with lazy create, but you just update ranges with the same value because
No,
only endpoints actually matter.
Initialize every single point in the seg tree with its index, and it should just work. Because because you're not doing like a range set, which is annoying. You're doing like a range add, which just works.
Yep. Do people understand it? If so, we'll move on to hopefully a
Can you please
harder
explain
problem.
the solution?
Sure. Does someone else want to?
Yeah, someone other than me like bring a different perspective.
All right, so so do you know the so the reduction from the points to the ranges, I'm going to assume you know that because it's been explained a few times. So once you have these ranges over the number
Yes,
line,
I
yeah,
understand.
okay.
You basically can reduce it so you have two ranges. So you have two problems where you are penalized for the maximum weight of the two ranges. And
Oh no, not two ranges, just one range for every point.
What range?
One range for every point. The range is just the minimum. The left end of the range is minimum of x and y coordinates. Right end of the range is max of x and y coordinates.
So the left end of the range is the minimum, and the right end of the range. I see. So you're sorting all the numbers by the maximum of their coordinates.
Yes, and then you sweep using the same thing, and you update. Like once you reach the right endpoint, you update where the left endpoint is, the value of the thing, the value of the range. Does that kind of make sense?
Oh, so so then I update the value of every range by doing what?
All right, so you know that okay, so once you sweep to a certain endpoint, you know that once you sweep to a certain endpoint and you're adding this new range, you know that any subsequent ranges that pass the left endpoint of this range is going to have to include the range you're adding, right?
So I'm given a range, and then
Yeah, you're just adding it to the data structure. And the data structure for each element it stores, if I was to start my range at this endpoint, what is the score I'm going to get?
oh, so you're trying. So we reduce it to the problem where the range, you have one range, and then you want to select two endpoints in the square.
Yeah, so you want to select a range, the left and right endpoints of a range, such
Yeah.
that the scores of all the point ranges that are contained by this range completely is maximal.
Oh, so you just want to maximize the sum of the scores in that range?
Yep.
Minus the length of the range?
Yep, minus the length, of course. But you're sweeping over the thing anyway, so it's fine. And also, you could just initialize. You could just initialize the points as well.
I understand that problem can be solved quickly, but I mean, how do you reduce it to that problem? As in, you try to sort by the maximum of their coordinates, right?
Mm-hmm.
But can't I just shift it 1 trillion units up? And
You coordinate compress them.
Oh, so how does it work? Like, because if I take the maximum of their x and the maximum of their y, and I just compress it, and I just shift it up by, then I add 1 trillion to the y coordinate, or 100 million in the problem statement, then it's not going to be correct anymore.
Well,
So you're basically sorting by the y.
Your square has to be along the y equals, like the corners of the square, the opposite corners of the square have to be along y equals x. So if you're shifting them all up, then, well, your square's going to be 1 trillion long anyway.
Oh, I see. So the square has to be touching the line of y equals x. Or does the square have to be touching the line y equals 0?
Oh,
No, only y equals x.
No,
So what is the rules of the problem? You try to select a square that contains as many points as possible to maximize the sum. However, it is small, and and the square also has to touch the line y equals x.
More than
Did you see the link? Did you see the link that was posted in the channel of the problem?
It doesn't have to touch it. It has to be like its axis of symmetry.
So I see. So it just has to have be parallel to the x-axis.
No. It has to have the y equals x as an axis of symmetry.
Oh, so it has to. Oh, I see. So it has to have y equals x as an axis symmetry.
So bottom left endpoint is xx, top right endpoint is y. Oh no, bottom left endpoint is AA, top right endpoint is BB. I don't want to use x and y.
I see. So it must have y equals x as its axis of symmetry. So then I want to select the leftmost point and the rightmost point of the x equals y axis. And then
we've already converted. Basically down to like a range problem. Into a 1D problem. So basically, what you're thinking of now is like the reduction, which you should kind of keep separate from like the solution that I described.
So I misunderstood the I was solving the wrong problem all along. I didn't know the square had to be symmetric on the x equals y axis.
Don't worry, man. I did the same thing on problem 1.
I can see why you're reducing. So basically, you have two endpoints on the x equals y axis. Sorry, the x equals y line. You have two endpoints. I understand that. And you're trying to minimize their difference while trying to maximize. Oh, I see. It's equivalent to just having having a rectangular square and then just having two endpoints, and then you try to maximize the element fit inside. I see.
Wait. So did you reduce to the same problem we had?
So what's the problem you have that you reduce it to?
I'll try state it again. Basically, you reduce it to like you've got a bunch of ranges on the number line, right? And when you cover the range, you gain whatever cost there is, right?
Oh, so when I cover range,
you gain whatever cost it is, because we convert the points into different ranges on the number line.
Oh, so I see. Yep. And then you have to touch that range.
You don't have to touch it. You have to cover it completely with your own range in order to get whatever's on the point.
Then you do a sweep line for it.
Yeah, you do a sweep line plus seg tree plus whatever kind of... Yeah, you do a sweep line and seg tree for it.
I see. I see. Yeah.
There's
thanks.
more details in the fact that you have to account for like the length of the line segment, but it's not too difficult to work out.
Thanks for the tip.
No problem. Angus?
Does everyone understand that? I'll present the next problem then.
You should probably call out someone. Does anybody have permissions to unmute?
Just checking, how many problems is there lined up?
I'm gonna go to a harder problem next.
Okay, fair.
Go to problem set and then like search up the rating and just increase it by 100 every time.
And that's pretty much what I did. This next one's
Big brain.
I mean, like for all the other ones, I knew the solution to them. The last one I don't, which I guess is actually the intention of visualization, is that the person running it doesn't know the solution. Well, we're jumping from 2,400 to 3,000. That's fine.
I think we've handled
Over 3,000.
Is that like
Okay,
IGM?
never mind. No, it's not.
Is that International Grandmaster?
It might just be, it's either IGM or GM. I'm not sure. Well, look, I had one problem in between, but you've kind of burnt through all the other problems. So
let's see the problem in between.
yeah, okay. So is everyone ready for us to move on?
Can we just get the 3,000? That'd be kind of...
Yeah. Once everyone's ready, we'll just go to 3,000.
Yeah, I want the 3,000.
All right, fine.
Okay. I'll present the problem now then. Let me just make sure I've got it correct. Yep, okay. So the problem is you have a graph, undirected graph, but weighted. So, and then you want to know the shortest path from node 1 to node n. So you have n nodes, m edges, n bidirectional edges, each will weight. You want to know the shortest path from node 1 to node n. However, you have a number of queries of the form change the weight of some edge to some new weight and report the new shortest path. Each query is independent, so the change gets undone after the query. And you want to answer all these queries. They're up to 200,000 nodes, 200,000 queries. So repeat that. You have a graph,
How
undirected,
many edges?
undirected weighted graph. You want to know the shortest path from node 1 to node n. You have a number of queries of the form change the weight of some edge to some new weight. Each query is independent, so the change is undone after each query. 200,000 nodes, 200,000 edges, 200,000 queries.
Wait, is it like, so the start and end are always fixed?
Always one and end. So the same path every time.
Oh, I see. Wait, hang on. Is that a bit?
That's just a problem.
I think you solved this
I'll
one.
send the link.
Yeah.
Here.
I think
Yeah,
Here
okay,
we
come on,
go.
just say nothing.
Have you solved it already?
we solved a slightly different one.
That had a much lower bounds, didn't it? Though.
Well, I solved it using that bound, so like whatever.
Yeah. It was like remove the edge rather than like change the edge weight. Does that change?
Oh, have you already solved it? If you've already solved it, I can get another problem. But hang on.
Good.
This includes changing edges of nodes that aren't on the shortest path. Does your solution account for that?
I mean, in that case, it's just a simple relax. Right?
Yeah.
I don't know this. I don't know the solution you have in mind. So
Okay, just it works.
all right. Sorry about that. I'll find a new problem then. You've already seen that one.
I don't remember.
I was like, there's a black box for deleting an edge, and like, you can handle the case of like at this edge instead. So like,
I mean,
No,
yeah. Sorry.
if I remember properly, my solution was E log V using all of the edges.
Then I'll find. Sorry, I'll find a new problem.
But what I don't think your solution works. I don't think what happens like when you decrease the weight of an edge.
Then like it's not part of the shortest path. So like you can just do whatever you want. Like, just include that edge, see what you get.
Oh yeah.
Trying to find problems that don't have a math tag associated with them. Alright, here's one.
Trying to find problems without a math tag associated with them.
Because they're mostly off syllabus.
We will make up for that in the ACIO Open contest. Don't worry.
Wait, are we calling it open or contest 3? I feel like we should just call it contest 3.
Open contest sounds more fancy.
Bruh, nah. Contest E for very E.
Contest E, because E equals 3 also equals pi, which also equals the square root of g.
This context is Bellman Ford because it is VE.
No. I'm saying it's a contest very E.
Just saying, people who are listening to the recording of this thing afterwards are just going to be very confused.
Yes.
I have a problem. I haven't read it yet. I'll send the link. We can read it and decide if we want to do this problem. Does someone want to read the problem and see if they think it's a good problem, and I'll look at other problems? Because all the other ones I had were easier, so we'll pick a hard one.
I think I saw this problem in like randomly searching what is the hardest problem on Code Forces. Right, and it's when I learned about like persistent centroid decomp.
Wait, was it this problem?
No, this is not persistent centroid decomp, but I think this was like pretty ridiculous as well. But I'm not sure. Like,
Has anyone else read
Persistent
it?
centroid decomp? Come on, surely retroactive centroid decomp.
Do you think this? Has anyone else read the problem?
I've seen this problem. I briefly looked at the solution and I couldn't understand it.
So, are you happy if we go through it now, or do you want me to pick a different problem?
I don't know. I'm trying to figure out whether or not it's the same as the one as I read.
So this problem is asking us to find like a subgraph such that each node has degree 1, 2, or 3, and no two adjacent nodes have the same.
Is that all it's asking?
Seems
Oh, also the degree of each node is different.
Let me double check because there was another problem that looked exactly similar to this. It was rated 3700.
Okay. I mean, if you don't know the solution, that's fine then. But if you do, we can move on.
That's fine, but I just want to make sure that we can like reasonably solve this.
Wait, and this is like tripartite graph.
Yeah. If you read the problem, does someone explain it?
Okay, I think I read it. I'm
Yeah.
not sure my interpretation is correct. My interpretation is that you have tripartite graph. There are some edges, and you're given like the tripartition, and like supposed to assign a number between for every edge that's 1, 2, or 3, such that for each two nodes which are adjacent, sum of the numbers between their edges are different.
So what's the condition? Can you repeat that again?
What do you mean by condition?
On the sum of the edges.
The sum of the edges for each two spaceports that are adjacent, the sum of the edge weights which are incident to each of the two nodes are different.
Okay. Okay, yes, I think so to make sure my understanding is correct, you have a graph, you're given a tripartition such that you're given like three sets of nodes such that every node's in one set and there's no edge between two nodes in the same set. You want to assign a weight of 1 to 3 to each edge such that the sum of the degree of each two nodes are different, or that over two connected nodes are different. Do people want to do this problem, or do you want me to find another one?
I think this is looks like a pretty good problem. That just me
Okay,
don't know about it.
sure. How about we all have a think about this problem then, and in a few minutes we can discuss. But if anyone doesn't understand it, feel free to ask questions. But if you do, let's think about it.
What channel is the channel where the problems are?
General.
General.
Thanks.
Jinx.
I've put the problem minus flavor text because I thought the flavor text was quite confusing in general. Tell me if there's a mistake in it. I think it should be okay.
Maybe I'll add the fact that there is at least one node in tripartition, and that the nodes are connected.
I'll add that. Yeah, I agreed. The problem statement was very confusing.
I really like the way Jerry worded it. There's so much less confusing. Like, I don't know. It feels kind of strange.
If anyone has any observations or ideas, feel free to share them. Yeah, the problem got 3 solved in contest.
Let me guess. Tourist, BenQ,
It was a team contest.
Tourist, BenQ, someone else.
300 IQ got it. None of your list got it.
Oh yeah,
But I think-
300 IQ.
And the first solve was 3.5 hours in.
TM William Lin 168.
All right. Maybe since the first solve was 3.5 hours in, we should move on to another problem. Since we don't have 3.5 hours.
Yeah.
I think we should keep thinking because, like, after all, we do
Sure.
have like many people rather than just 3.
That's fair. And even if we don't get a solution, we might have some ideas.
I don't have any idea.
All right. How about one subtask is one of the components has size 1, or even 2 of the components have size 1. Think about that case.
Don't give up, guys. As von Braun once said, even if you reach for the stars, even if you miss, you will hit London.
Okay, that is. This is being recorded. You realize that, right?
You hit what?
Just ignore that. Okay.
I'm digging through the recording to find out what he said. Just tell me now so you can save me some time.
No, I'm not going to repeat what he said.
All right. So how about you think of first subtask, if you want to, is that 2 of the components have size 1, and see where that goes.
I don't know, but like I'm pretty sure that's a bit too easy. Because if 2 of the components have size 1, then like
Yeah.
okay, so first of all, if the remaining component has less than or equal to 6 nodes, then like you can essentially just brute force.
What you can just do is you can just assign order out. Suppose
You just brute force.
suppose
And if it's
no,
large,
this
then
is even easier. This is even easier. Suppose
Okay,
component 1. Okay, for 1, if there's like exactly 3 nodes, like 1 in each component, then you have to do 1, 2, 3. Otherwise, then what you can do is suppose component 1 had is the one that doesn't have size 1, then you can just assign all outgoing edges to be like 2, right? So then each oh, it doesn't work.
I mean, you can just assign assuming n is large enough, just assign every node 1.
yeah.
Consider the
that's
case
what I'm
where the 2, and one breaking case is if the 2 nodes are connected, like the 2 independent ones are connected and they're the same amount of degree, set one of them just to weight 2.
Yep.
Okay, that was a bit easy. New subtask. One of the components has size 1. Also, feel free to think about full, but I think have to start somewhere. So one of the components has size 1. The other 2 components can be whatever they want.
Can we just appreciate that the contest was called Bubble Cup?
I have like dumb ideas.
Feel free to share.
One of them is like BFS from node and do the one node, the component with one node and do something. I think that has some other promise. The main idea I'm thinking about right now is just mod 3. Like one of the components have all labels 2 mod 3, another component has like 0 mod 3, and the third has like 1 mod 3.
In terms of what you want to assign the total edge weight to be.
Like the total edge weight is like.
I think that second idea is quite promising. I guess gives. I don't know, but it could lead somewhere. So the idea is try and get everything in a component to kind of add to the same thing.
Actually, I think mod 3 breaks just by itself. Because of the fact that if you have like 3 nodes in a line, then.
Or is it like, it's impossible in some cases?
No, it is possible actually. Yeah,
What was
no.
your breaking case?
Never mind, forget what I said.
Oh, you just like assign weight 1 and 2, right?
Yeah.
I mean, it shows that you can't arbitrarily assign mod 3 values to components.
Yes.
Unless you can.
I don't think. I mean, like you may as well assume you can because you just tried all 6 permutations.
Oh yeah, sure.
What if there was only 2 components? What if it was like, yeah. What if there was nothing on the third planet, even though this is not like a sub-problem? Surely it's strictly.
And yeah, I guess we can try and solve that with 1 to 3, or maybe even try and solve it with 1 and 2 only. Like I'm not sure if that exists, but maybe it does.
Yep.
So we're solving the alpha interplanetary system problem. We're solving it, right?
Yes, and I think below the link I wrote the problem again in.
Yeah, this is quite demotivating to solve because I pretty much have
in not flavor text.
I wonder if it's NP complete.
I mean, clearly it's a programming context problem, so like.
It shouldn't be NP complete unless P equals NP.
I mean, it can be NP. It could be an exponential time algorithm, but the constant factor is 1 over 25 trillion trillion trillion.
Indeed.
Yeah.
Have we ever seen a problem like that?
I don't think 1 over 25
Trivial
trillion
bit set of bit
trillion
sets.
is enough. Even if you have 2 to the n, you'd have 1 over 25 trillion factor would become impractical when n is 200 for 2 to the n.
Alright, it's 1 over Graham's number.
Or what happens if it's 1 plus 10 to the minus 5 to the power of n?
Very true, very true.
Or 1.01 to the power of square root n.
I'll be back in a second.
Hey, does anyone want to try to prove that if we have a cycle, we can assign arbitrarily any mod 3 value can assign arbitrarily?
What do you mean arbitrarily?
Basically, if you say, okay, node 1 is 0 mod 3, node 2 is 2 mod 3, node 3 is like 1 mod 3, you guarantee that there is assignment of the cycle edges, connecting them, that there is a solution.
Have you constructed for 4 and 5?
That could totally work. Yeah, I buy that.
I think it works for n equals 3, like a triangle, but I'm trying to think if it will work for bigger values.
I mean, you can just, I believe, like you can like procedurally remove cycles by just like having them, just like set them all to like 3 or something stupid, right? Until like you have.
Not really. Actually, my idea is very similar. You remove the cycles. At the same time, you mark the nodes adjacent to the cycles you've removed as can be anything.
I mean, what I'm thinking is like, if we remove, okay, in the tripartite graph, what is the smallest cycle we can get? I mean, what is the smallest cycle we can get that we can't remove? And
What do you mean? We can get a 3 cycle.
as in like, if you remove it, it breaks the graph. If you remove it, then the node will end up like what I'm saying is like, if you can procedurally remove cycles and reduce it to basically a tree problem or something very close to it, it might actually like help us solve the problem. So what I'm thinking is something like asking first, what is the smallest, what's the most tree-like graph we can get?
Well, I mean, if you delete all the cycles, then you took the forest.
Sorry.
Yeah,
What
but if you get like a
miss?
forest with like one node on its own, then you can't really do much to it, and we kind of don't want that. Does that make sense? So like we want to try make a tree if we can, and I'm trying to figure out like under what circumstances is that not possible.
Is this for the case, the full problem or the subtask of it?
The full problem. No, just throwing some ideas around.
Yeah, sure.
Yes, I've
How does
proved it for all cycles.
removing cycles work? Sorry.
Like basically, I think I just proved that if the graph is a cycle, then you can assign for every assignment of a modulo to each of the nodes, then there is a satisfying assignment.
Oh yeah, I just did it as well.
So what's the proof?
Proof is like, okay, so like you suppose you fix the value of a random edge, right?
Yep.
And like you can logically deduce around the cycle, and there's like one edge you have to satisfy, right? Last edge you have to satisfy. Basically, you observe that we can choose the value of the first edge we choose to satisfy that node, to make that edge satisfiable.
Okay.
Basically, in that case, we can now have some cycle removal agenda. Like, I think something like greedily remove cycles until like fizzle gone. Patrick, what do you mean by triparity BFS?
So I guess I'm not sure if this has been said, but if you remove cycles and then left with a tree, if you can remove cycles in such a way that there's a tree remaining, it's fine, isn't it?
Yep. Okay. I made a construction for all cycles, I think. Like,
Okay.
so I guess I can briefly explain my construction. Suppose the cycle has an odd number of nodes, right?
Yep.
So pick a node, right? Let's say, yeah, okay. Pick a node, and then the two edges that lead out of it. One of them is 1, the other one of them is 2, right?
Is this for general case or for or
Just for odd. Let's do odd number of nodes first. Then I'm going to go to even number of nodes.
and like modulo anything?
I see it. I think I see a full solution. By the way,
Just
let's
like
go first.
Odd number of nodes and even number of nodes. So like, just assume you have a cycle with odd number of nodes and even number of nodes. I'm going to output a construction that works for it. If that kind of makes sense.
Yep.
So what you can do is you pick a node, and then the two edges that lead out of it, one of them make it 1, the other one make it 2. So like the node has sum 3, right?
Yep.
Then the node that lead out of it that has value 1, you set the other edge of that node to 3, so that one has value 4. I mean, that one's a sum 4.
Yep.
And for the other one with value 2, you also put out an edge with value 2. So that node is value 4, right?
Yeah, and then from there you just.
And then you go 4, and then you go 5, and then 4, 5, 4, 5, and so on.
Yeah, it's kind of alternate. Yep.
Yep.
Makes sense. And even kind of.
Sorry, I mean left one is 4, right one is 5. So 4, 5, and then 5, 4, and then 4, 5, and then 5, 4. So that when they're joined together, you just put any number there, and then like it will always work. And for even cycle, it's kind of a similar thing, except you have 2 nodes at the start.
But how are we going to remove cycles in a way that like make sure we don't accidentally undo our hard work?
I think I just an interesting idea.
Yes.
So basically, consider consider the case where the thing is a tree, right? And
yep.
Suppose we pick a root.
You can just do it.
You can just do it by greedily assigning, right?
Yep.
Now consider the case of the cycles, right? We claim that just delete all the cycles, so we're left with a bunch of forest, right?
Yep.
How we satisfy all the trees, like whatever, right?
Yes.
And now, because we know we can like make a cycle do whatever we want, just make the cycles do whatever we want. Anything that's completely broken.
But if a cycle just saying it isn't broken and it intersects with another cycle, we just say it isn't broken, then like the intersection might be broken.
My thing is just basically you delete a cycle, you greedily find a cycle, delete the cycle.
Define delete.
You just remove the edges.
And what weight do you assign to them?
Assign them like ones or something. I don't know.
Just all the same weight.
Sure. like all the same weight or something.
And I kind of race, because if you have like a vortex graph, then nope.
Actually, no, my bad. Sorry, yeah, I reminded myself of what I'm going to say. You know, like, suppose you have the values of the tree, right, already assigned. Then I claim that you can satisfy all but one of the values, right?
Wait, so say that again. If you have a tree.
Have a tree and you know the values that you want to assign to the nodes in the tree, right?
Yep.
And
So like X mod
easy to
3.
satisfy all but one of the values, right? Root being
Satisfy,
the value that you might not satisfy, right?
considering only nodes in the tree, or considering
Considering only nodes in the tree.
edges in the tree? Yeah. Sure.
So now consider what happens when we delete a cycle. We might make a bunch of forests, right?
Yes.
And for each of the forests, at least one of the nodes in the forest were originally in a cycle, right?
Originally yeah, sure.
Which means that we can later add our cycle in and change the node that wasn't originally satisfied into whatever we want because of the cycle lemma.
Can you repeat the cycle lemma again?
Given a cycle and a modulo 3 for each of the nodes in the cycle, we can pick edge weight. We can choose the weights of the edges in the cycle such that modulos are satisfied.
Given any modulo for each node.
Given any modulo 3 for each node.
Yep, I see where this is going.
Basically, greedily delete cycles, make the forests, you make the originally cyclic nodes in each forest. Root, you satisfy everything but the root, and you add the cycles back to fix it is broken.
Wait, why does like modulo 3 make it so that it satisfies everything? Because wouldn't knowing what modulo it is with 3 kind of be important? I mean, no, like wouldn't knowing the rest of the number kind of be important?
No, it wouldn't be. Not really, because so say we make planet X, all of planet X's edge weights 0 mod 3, planet Y's weights 1 mod 3, and say all of planet Z's weights mod 3, right? And then clearly, because edge connects node to a node of the same tripartition, it means that you either connect 0 with 1, 0 with 2, or 1
okay,
with 2.
Yep. Okay, I see. Yep.
And if it doesn't work, we permute the 0, 1, 2 around until it does. To our guaranteed solution.
Yep. It would probably take a while to think about implementation, but that I think that solves all.
I hope it does anyway.
I think it does. I think it does. Anyway, I'm not going to implement that. Are you?
It's not. My backlog's pretty heavy.
What was the solution?
So you kind of solve. Okay, so you remove all the cycles. You solve for all the forests. So you figure out like what mod 3 each node is. Wait, no. Wait, what do you do?
You want to fix. Don't you want to fix each node's mod 3?
Yeah, you want to fix each node's mod 3. You want to find all of them. And then
like given a tree, you can essentially do whatever you want to every node except the root.
Yep.
So we're going to give all the first components 0, all the second components 1, all the third components 2, mod 3 in each tree in the forest. And then with cycles, we can fix up the root because you're guaranteed there's at least one node in each. There's at least one node in each forest, which is part of a cycle. So then you can kind of fix up the roots with one of the cycles they're in. And then every other cycle make it so it doesn't change anything.
Yep.
I guess one case is. The one case it doesn't work would be the original graph is a tree. But you can probably just do it in that case.
You have
Do it.
less constraints than if it wasn't a tree. So yeah.
I mean, it.
Or true, because then it's just bipartite.
Nice. Up guys, we managed to beat Forest.
Alright.
I mean, I guess
We
perhaps
haven't implemented.
It's a cute
We-
contest name for an ugly problem.
we haven't described how to find a cycle in a way that's like order n.
Wait, cycle finding.
Just DFS tree and like everything will work out.
Oh
Because you
hey,
need every cycle. Does every cycle need to be? Every cycle need to be
You just have
disjoint,
to
right?
subtract like a few cycles, so like the remaining result becomes a forest, and with, like DFS tree kind of works for that.
You kind of pick a DFS tree, pick one.
You
pick a
pick
DFS
a few
tree.
cycles, and then as long as
pick
there's no
one
more
cycle.
cycles.
I mean, because you need each cycle to be like disjoint.
Yes, well, yeah, but also once it's disjoint, like any other cycles that interfere with it. Okay, no. Oh wait, hang on. Yeah, so. Oh, I see. There's a bit of nuance in it. Interesting.
I think maybe you can like pick some sort of cycle, then recurse on subtrees.
Yeah, if you pick a cycle, then any other cycle that intersects with it, you kind of don't have to worry about, except you kind of do.
I mean, because like,
Oh yeah. Yep.
because there could be
You
because
can have cycles like go into a node and then go back out of the node and kind of use.
and there could be cycles that like jump over the cycle that you chose.
Nah.
No. Actually, that's actually easy. That's not bad to like. That's not bad to process though, because once you pick the cycle, the choice is final, right?
I mean,
Any final result is valid. So you just do it, and then you can just literally just record in like a global state. Oh, which cycles you've taken, and then if you go up, you can just go like, oh wait, my last cycle was at depth this, and then it's like, oh wait, no, this isn't a cycle. It's fine. I'm fine. Unless the components are connected again.
I'm thinking,
I'm
what if you
thinking-
do something like pick the biggest cycle in the DFS tree, and like if that cycle is of size greater than n on 2, then you're fine. If the biggest cycle is of size less than n on 2, maybe you can do something else.
Mm-hmm.
Because like if it's greater than size n on 2, you can just literally reroute and start again by like principle of you removed half the edges.
Okay, what I'm just thinking is like if you go from the root downwards, then you can probably like make a bunch of guarantees. Like for example, you won't have nodes go into the cycle and then back out of the cycle that you're looking at because of how you're looking at it. Nah, that doesn't make sense. And you kind of have to account for stuff within this. Like if you're trying to like traverse down a really long cycle, you still have to like consider all the edges within, like all the cycle edges within. Like they don't just magically disappear. Like you still have to assign them something. So you'll.
we agree that we have polynomial time algorithm so far, right?
Yes, it's just the question remains: how do we pick some cycles that are all disjoint such that we're left with a forest?
I'm thinking Euler tour.
Perhaps so.
Or Eulerian circuit.
Yeah.
But like, how do you make sure that that is of sufficient length?
I don't know. It just seems missing.
By the way, isn't longest Eulerian path also NP complete or
I'm
NP hard?
I'm just thinking.
All
Uh,
Alarian paths are the same length because every edge.
Okay,
Basically,
no, longest Eulerian subgraph path.
like
Wait,
what
what's
I'm
an
thinking,
Alarian sub?
you add edges.
Yes, the longest walk. So like the longest walk in the graph that uses the most edges. That seems
It
NP
uses
hard.
every edge at most once.
No, uses the most number of edges.
Is a condition on how many times an edge is used?
Once. At most once.
That's Hamiltonian cycle.
Yep.
Or so I guess it's not because no
It's-
could repeat it
I
twice.
think it's trivially reducible, I think.
Yeah, like turn nodes into edges or something, and you should be fine. Or edges into nodes. Yeah, if you turn edges into nodes, you can probably make it all Alarian into Hamiltonian path. So like, I'm thinking the lines of square root decomp. Maybe this works. So like, do a DFS tree, right? Take the biggest cycle. If the biggest cycle is of size greater than square root, it's fine. If it's smaller than size square root, can we do something? It's like the same as the idea I presented before, but with square root decomp instead. Because in that case, if the biggest cycle is of size less than square root, we can afford to consider every single cycle in the DFS tree. But that isn't necessarily every single cycle in the graph. So that isn't necessarily sufficient.
I remember I heard somewhere like this is like a graph theory nuclear weapon, but like delete all the bridges, then I heard of something called ear decomposition that can compose a connected graph.
Oh, what?
Ear decomposition, I have not much clue what it is.
Yeah, I've heard of that. I think ear isn't like the ear on your head.
Yes, I know, but just
Not the ear in our heart.
Just assigning edges randomly. What could go wrong?
Good fun.
I think I might have an n root n that might be able to optimize more. I don't know, but it's might be a bit cooked, but I think it might work. So pretty much the idea is take any DFS tree, find the highest back edge, the back edge that goes up the most. If this back edge goes up more than root n, we can essentially just afford to remove it and repeat the process. Because if we did this root n times, we would beat n root n overall. Consider the case where the biggest one is of size like less than root n. Essentially, we're just going to, the idea is take some back edge, remove its cycle, and then like make the new DFS tree, but in a way that's only order size of cycle removed. I think you can kind of do this by consider the range of nodes in the cycle you removed. Find the one with the lowest back edge outside the cycle. That'll be the new node that is in the DFS tree. And then just like do a mini DFS within that. And then add the new subtrees onto it. And maybe handle back edges into this new DFS thing. And it might work. It's a bit messy.
For the problem, an algorithm that runs in time complexity n squared n for 200,000 take about 89 million. So it might be borderline.
It might be borderline. I also haven't worked out details. So it might not work or it might be a pain.
Do not
But
know
it's
what
kind of,
constant factor it would be, right?
I mean, if it works as I think, it'd be a fairly low constant factor because it's kind of DFS constant factor. But implementation constant factor might be quite high.
Comment. I think a little while ago this was rated like 3700. Like
I mean,
I don't know
we've done
why
it.
but all the problems rated 3700 are like gone.
I'm not sure. I mean,
They were recently re-rated.
Yeah,
it's
yeah,
good.
yeah.
It's good that
This was like one of the
John.
hardest problems. I just looked at it and was like, yeah, I wonder what does the top of the top look like.
I mean, I guess it shows that you can solve harder problems because we're close to it. Because I mean, if luckily John did his motivational speech and we chose to stay at this problem. I guess I'm probably gonna head off in 5 or 10 minutes, but you can keep thinking about it. I guess.
Surely do cost. Okay, never mind.
I mean, we still haven't like. I think. I mean, you're free to do whatever you want. At least while I stay here, we'll keep thinking about how to do this problem fast, and then if we don't solve it, it'll remain an open problem, I guess.
Okay, so we solved a problem that there's a graph, and the graph wants us to form a pairing of edges or something so is it correct that you can that you have the operation of making a flight between two nodes? And each node can have 1, 2, or 3 flights, and no two neighboring nodes have the same.
Also, the graph is tripartite.
So they also guarantee the graph is tripartite?
Yeah, so read what I just resent in the general chat.
Yeah, they
Hopefully
guarantee there's such a solution, hence the graph is tripartite. Do they show you a tripartite decomposition of the graph or like a three?
They do. You're given one. Because finding one is NP hard.
I know.
Oh yeah, duh. Because like it can be equivalently said that it's like three color rule. Oh, I can't talk today.
What did I miss? I went to 4, 5.
Oh man, I kind of regret ditching English. The stress is setting in. I know this is being recorded, but like, wow.
Feel free to go do your English.
Yeah.
So like the idea presented before that claimed was n root n. Actually, there's no reason why it would be n root n. It would, if it works, it'd just be order n.
I kind of like lost
Wait,
track
what?
of all the intuitive proofs and
So like,
the approach we're taking.
But you know how three coloring is NP hard?
yes,
There
I
are
have
cases where finding a three coloring can become easy with certain restrictions. Or in P, for example, what if I restrict the graph such that if you three color, you're only allowed to use one node of the color 1?
can I do some idea based on Angus's spanning tree?
yep,
So consider an arbitrary spanning tree, and like consider the non-tree edge. Okay, first of all, let's just delete the bridges, cause like screw bridges, right?
Okay.
sure.
Now the graph is by edge connected. Okay,
Yep.
arbitrary spanning tree. And for each non-tree edge, you take the LCA and consider the highest edge, the path.
Wait, say that part again. Sorry.
So consider the highest edge in the cycle formed by each edge with the DFS tree. Routing arbitrarily
Yeah, that's just the top of the back edge, isn't it?
at the top of the back edge. My greedy idea is something like use the edge with the highest back edge and delete it.
Oh, I see. Interesting.
I don't know what I make of it, but I'm just putting it out there.
I mean, that would mean the component is rerouted from somewhere below, if that makes sense.
Wouldn't that actually make it like better? Because you know that you're going to delete that component like from all the way up on the LCA. And then once you remove a component, it's fine. You've removed it. You don't have to backtrack or anything. So you've removed it and you just keep track. Oh, you've removed that. So like when you move to children node, you know exactly where you should move to and where like which nodes, which edges have been taken.
Yes, if it's the highest, like the highest back edge, then you're guaranteed that above it, like if you consider above it and around, that's a new component because there's no high back edge. So you can kind of do that part separately.
Okay, so like yeah, go ahead.
I mean, you can go. I think I've got an idea. The
Okay.
idea is essentially assume for now that the root has at least 2 children and that both the children have actually, it could be broken. You go, sorry. I think my idea is broken.
Rip. So what if we just stored each up edge? Wait, no, it's back edge. Sorry, back edge. In the tree, and then we kind of just record because each back edge corresponds to just like a path up the tree, right? Like on the actual tree, it corresponds to like a path of tree edges that goes upwards. What if we kind of keep track of the edges that we have already taken? If that kind of makes sense. So like we're already like preemptively splitting it into subgraphs. Oh wait, no, it doesn't. It doesn't actually work according to the previous. According to the problem stated previously, it doesn't actually work.
All right, here's an idea, which actually it might work. So it's the idea from before. Assume that then the root has at least 2 children, and both of these children have back edges in the subtrees. Assume it we're going to consider the highest back edge, the back edge that goes the highest up the tree. Because if you consider the back edge that goes the highest up the tree, we can split into 2 components. One of them is like above it and around in the tree. And in that case, that DFS doesn't change because there's no back edge to that part of the tree. And then everything below us in the subtree, because when we remove some edges, we're gonna like mess some stuff up. But if we pick some back edge such that the part of the subtree we mess up is of size less than n on 2, we can essentially just like remove the edges and restart that subgraph.
Oh, sorry.
And overall, so for now, let's just say we're going to take the back edge, which finishes the highest up in the tree, if that makes sense.
Up.
Let's call that node U, the node which the back edge goes up to. Let's split the tree in 2. Half the tree is all the nodes in U's subtree that contains a back edge. So like if U has multiple children, consider the subtree of the child which contains the back edge, if that makes sense.
Right.
And then consider the rest of the tree. Claim the rest of the tree, if we were to redo a DFS and just remove the subtree at U which contains a back edge, the rest of the DFS should look identical. Proof, there doesn't exist a back edge which goes above it in the tree, which essentially means that we've reached an articulation point. So removing that graph from the tree won't change anything. Okay, so the claim is, as long as the root we choose has at least 2 children, and both those children have at least 1 back edge in them, consider 2 back edges, claim one of their subtrees must have size less than n on 2, reason they don't intersect, therefore they can't both have size greater than n on 2. Take whatever one is smaller and just like cut it from the tree, remove the cycle and redo that subtree, and then repeat process on unaffected rest of the tree. Some issues with this, it relies on the fact that there are always 2 subtrees of the root which both have back edges in them.
I don't think I'm quite following. Probably I'm a bit tired. Probably a good time for me to go, actually.
Yeah. Sure.
I do apologize.
No. I think another way of phrasing it is pick an articulation point. Pick the side of it which is smaller, remove a cycle from that side, and then restart. But because the size of this tree the size of the graph you're considering is always halving, it's n log n. That might not make sense. It's kind of hand wavy.
Well,
But you can go.
like you're doing something similar to a centroid decomp.
It's essentially centroid decomp, but we're guaranteeing that our centroid is articulation point and isn't necessarily a centroid. But yes.
Just one last idea. If we do a legit centroid decomp, then what would happen? Like
Fair
pick
point.
the centroid edge, you find a cycle, that contains that edge, take that cycle and you break it into 2 smaller subtrees.
That assumes that the 2 smaller subtrees don't have an edge between them, right?
Yeah, that's. I guess maybe. Also, people might want to look into a decomposition that looks promising. I just read the Wikipedia. What? Let's see. Night, guys.
No. Actually, I think the articulation point decomposition might just work. Essentially, find some articulation point. Articulation point being a point that, if removed, disconnects the graph. Claim we can like essentially remove that. We can essentially like split into two halves. Like one side of the articulation point and the other side the articulation point. The side that's smaller, we're going to recursively just like create new instances of the problem, and on the side that's bigger, just do the same thing but pick another articulation point without any more pre-comp. Anyway, I'm going to head off now. But I think we made some good progress.
There's an articulation point in that subtree. I mean that, like the other one.
Sorry.
Like, is there a guarantee that there's an articulation point at that subtree?
There isn't one.
Like the one that's in the bigger component.
Is there a guarantee that there is one?
Yeah.
I feel like there might.
Also, the tree we're using is a DFS tree, right?
Yes, which gives
Okay.
neat conditions on back edges. Does every graph always contain articulation? What are conditions of articulation points?
Definitely not every graph contains articulation points.
No.
I mean, complete graphs don't contain articulation points.
True. So I guess we need to do something. If this solution works, we need to do something in the case where there is an articulation point.
Mm-hmm.
Yeah, I'm gonna head off now. Good chat anyway. I guess I'll probably think about it some more tomorrow because it's interesting. But if anyone does solve, I guess share a solution.
Is this the
Alright.
last tutor session before like selection exam?
I'm not aware of any more plans for any more, so it may be the last one. Yes. Because I mean, selection exam is Sunday.
Is Kevin gonna write anything about it? Josh did like a whole brief like beforehand about like no pragmas and stuff. Remember last year?
Yes, because we're going to send. Obviously, because I mean, what has Kevin sent rules yet? Probably not. Because obviously, it's,
yeah, there's no rules right now. I don't like.
Yeah. So
we
before
notes?
I'm not going to say because we've got the rules decided, but I'm just in case we change it, I'm not going to say anything about that.
Right,
but because of the fact that it is no supervision, we're going to have a big dump of rules because we need them. And I guess maybe some.
What do you mean, like dump?
As in, like also stuff from like because in Fario there were some issues when it went down with what people did, and so what is the protocol when CMS goes down, for example? Which hopefully it won't, but the protocol is keep work like inform us. So like, I guess perhaps call Kevin or send an email to one of us, but then keep working as if CMS was still going. Because some people, there was some confusion when Fario went down, for example, and we don't want that to happen in selection exam.
All right.
The benefit is if it does go down, because everyone's seeing it at the same time,
everyone gets extra time.
It goes down for everyone. Yeah. Hopefully it won't. Like our goal is for it not to crash, obviously. But yes, rules about notes will be clarified.
Do you have like an idea of when? Seems pretty important.
I will get because I don't want to say it now.
Yeah.
But
as long as it's not like Saturday night
We won't do it so that it'll be. I'll give the guarantee now that we're going to send rules before Saturday, so that could be Friday night. But you'll have all of Saturday with the information.
All right.
I'm going to make sure that happens.
Nice.
Which gives you Saturday to prepare any notes if they are allowed.
Mm-hmm.
Any other questions about do you have any other questions about the format that I can answer? I guess obviously no communication, no Googling. That's fairly obvious. That will be in the rules, but you obviously can't message other people during cycling exam. That is highly illegal.
Practice contest. Logging with other person's details.
And obviously, we won't do what we do for trial exams and give everyone's password.
Bye.
That'd be an interesting. Bye.
See you later.
But yeah, for everyone else, hit.
Hmm.
All right. I'm gonna head off then.
All right. Cool. Thanks for this. See ya.
Yeah, all good.
Why are you here, Pat? He just left.
No, I didn't. Discord just crashed.
Well, he just left. We had okay. Did you hear about the part where he's gonna announce sell-in rules or something?
Yeah, I hit that. Oh,
I think that's it.
Chrome also crashed.
Did you go to crashchrome.com or something?
Yeah, I hacked Google.
Google hacked you. More like.
Suppose so.
Why is Jake? Jake, are you still recording?
No, remember he left. But he said he was going to keep the recording going.
Oh, I see. Oh, rip. Okay, we're still going. I see. Jeez.
I suppose Jaki's just going to stay here until he wakes up.
Interesting. Stays here until he wakes up. That is some 300 IQ plays. You have to sort through 12 hours of footage the next day.
Yeah.
Dang it, there's no music bot.
God damn it. Why is there no music bot?
Just play some music while Jaking is recording. Clearly the optimal strategy.
We could play a 10-hour version of, I don't know.
10-hour version of something that loops.
Something that Jaki wouldn't want to hear.
10-hour lecture on crown decomposition.
What are we doing in here? Oh, hi.
We're trolling Jaking. Right, so he's left his computer on. He said he's left, but he'll leave the recording going. So we're just gonna continue commentating as if it's still going, and hopefully he doesn't notice it in the edit, and he doesn't cut this part out, and it's gonna be so hilarious.
What things are we saying?
I don't know. Do your mouth clap me channel theme or something?
I can Rick roll. Wait, hold on. I recently learned this on piano. It was so worth it. Now just watch me get ACIO copyrighted.
Yeah, it'll get copyright claimed. Someone should have been saying copyright all throughout you playing that song. Because it's a parody. If you just keep saying the word copyright, apparently it's a parody.
What do you think is like the song that's like easiest to get a copyright strike on?
Surely
Copyright,
anything
copyright,
Disney.
copyright, 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 copyright.
You know what it is, right?
Oh, you're live.
It's
Here we go.
It's like Chainsmokers, but like it's like 3 notes.
What?
That was Chainsmokers.
Ramsey theory for metric spaces. Ah, yes. Ah, yes. Hold on. If I'm not in the recording, if I'm not in the stream, if I'm not in the stream, I don't.
Okay, this is what we're gonna make Jakingi watch for the next.
No, he's not
2
in the
hours.
stream, so like he can't hear it.
Yeah, but if he's keeping the recording going.
I will explain this.
No, like the recording doesn't work though, because he's
so
not in
yeah.
the stream.
Every
So you just followed your own plan there. What a
Oh,
shame.
come on.
What are you guys doing?
We're trolling J-King because he's leaving the recording on, so we're just gonna like continue speaking as if nothing happened. So like when he edits this footage, he'll realize he won't realize that like Angus has left like a long time ago, and we'll just like leave this part in, and it's gonna be so hilarious.
Wow, that's pretty poggers, I must say.
Yes, it's an elaborate prank.
Just got
Wait,
pranked,
Jakingi's
bro.
actually in. He's watching my stream.
Wait, what? Hold up, hold up.
What does it mean? It means
Hold up. Hold
Remember
up.
the-
Wait a second.
the terminology.
Wait, he's in the stream.
It means that any finite dimensional
No,
space of
okay,
L2,
you know
which is
what?
just
No.
N to N, the n-dimensional Euclidean space, any finite dimensional, for any Banach space, you can find in it
Oh my god.
finite dimensional,
He's even
any
laughing
finite
his head off
dimensional
right now.
Euclidean space with small distortion. This is actually as a subspace. You can find it as a subspace with small distortion 1 plus epsilon. For any
Oh
epsilon.
wait, hang on a minute.
I don't know. You can think about it. You can appreciate this is beautiful theorem.
I'm not sure the comp geom problem I posted in comp_geom is actually solvable. I think it is solvable.
Euclidean section. Oh, yeah, I will. Let me write it in
I
another
don't know.
way.
Way.
Quantitative form.
Wait, hang on. Are all the points are integer coordinates?
Not necessarily.
That's so sad.
Well, I mean, sure, why not?
Okay, if there were integer coordinates, I have an n to the 4 solution.
This is by.
And what's that?
Pick's theorem. Brute force every single point and find if it's inside, outside, or touching the polygon. And then you just use Pick's theorem.
Oh.
For every epsilon.
Wait, hang on. Does that work? Does that work? No.
0.
Oh,
Sure,
no,
you can
'cause
do
the
it.
intersection could be like at non-integer coordinates. Oh fuck. No, it doesn't work.
That's that.
You could wait. Okay, sure, you can do it if polygon convex. Like that's like
For any
trivial.
N, and for any n-dimensional
I mean, if they form a Venn diagram,
norm
I don't know.
space,
I mean, it basically is a Venn
Oh yeah,
diagram.
because the intersection is always a convex polygon anyway. Wait, hang on, is that true?
there exists.
Hold up. Is the intersection always a convex polygon?
Yes, it is.
Alright, seems good.
Dun, 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 dun.
Hold up, I have the best music right here. Okay, anyway, yep.
Is that Prank Patrol?
Yeah, that's Prank Patrol. Well, because of Marcus's DP lecture.
You know, I'll stream this, see if it works.
Stream prank patrol.
Stream my OneNote.
Ah, yes. Yes, it's working. Polygon.
All right, where's my pen? Hang on.
Also known as cost 2.
Hang on, I still have my Ramsey theory lecture going on.
Okay, you know what? Considering Jakeen's recording, I'm gonna put this on the record, right? If I ever become a tutor and I do a beta variety lecture, the first one I'm gonna do it on is cost. I'm gonna spoil the problem. Or maybe I'll only spoil part of the problem and you have to solve the rest. I don't know. Ryan's blog. Hold up. Do you have his entire blog stored on? Oh.
Yes, I've got. What else do I have? I have this.
According to Tunan.
And then I've got some problem statements that I hacked.
Okay, that was worse than the freaking, like, that was worse than the PDF conversion for, like, arranging plants.
Yeah, okay, wait, do you remember that, like, 2-day period when Kevin made a new ORAC?
Yeah.
Yeah, in that period, it ran slightly faster than regular ORAC, but it had slightly less memory. And because I was getting a single TLE on, I think it was Jim Thomas, it AC'd on the new ORAC, and then I just brought down the problem statements so that when it went down, I could still have the problem statements. Hacks.
Okay, it's a good problem.
Roger King is actually watching.
Yeah, dude.
So, all right, back to the problem.
He's actually recording this whole time.
Okay, so like, basically, I had, basically, if you have a bunch of points, it was while I was, you know the CompGeom problem that like it goes like this, and you got to find the area.
Mm-hmm.
Basically, it's like that. So, if you have, actually, no, this one connects to this one. Yeah, no, it doesn't. I lied. This one connects up here. Okay, basically, you just do the algorithm for line intersection to find the intersection here and the intersection here. And then basically, when you have your Venn diagram, this is for the convex case, by the way. You just have this one, and then you switch onto this one, and then you continue around. Actually, no, that's just a terrible diagram. This continues up, down here.
Yeah, I get it. Yep.
Yeah, whatever.
Well,
and basically,
twice the area of the intersection.
Well, because you have to output this area plus this area plus this. You have to like. Well, you have to find this area, and then you have to find this area plus this area.
Yeah, so like you can just like from the union area you can subtract.
Yeah.
Oh, yeah.
Okay. Now. Okay, I'm not sure if this entirely works, but so basically, the case that I drew up was like this. Let's make it a bit more. Okay, like this. So basically, the problem was you have to find the sum of this area, and this area, even though this area has no polygons that actually touch it.
Yep.
Okay. So basically, firstly, detect all of these intersections.
Yep.
Secondly, like
you kind of have to
like
find
observe...
a hole.
So?
Wait, no, continue. Never mind.
Okay, cool.
Don't worry about it.
And then basically, you've got like sort of like this planar graph. which is also bipartite.
Oh, I see. Oh,
Okay.
very nice, very nice, very nice.
Okay. Second thing we're going to do is got my pen. Okay. Second thing we're going to do is we're going to create a graph of connecting intersections. So we've got like a square over here. And then you've got one that sort of
I
connects.
just realized I was unmuted the whole time, so you hear my delicious typing sounds. Sorry.
LML. Okay. And then we've got basically another. Okay. But the thing is, if we add in the additional edges, so if you see that from this node to this node, there are two paths, like one that goes in, one that goes up here.
Wait, two
If
paths?
we, so one path that goes here,
Yep.
and one path that goes down here.
Oh, yep.
Cool. So if we added all those edges, then we have a bipartite graph. Every single node has 4 outgoing edges, because in the problem statement it also says that no 3 points are collinear, which means that you can't have situations. Oh, that's not what I wanted.
Wait, hang on. That graph isn't the graph that you did up there. Looks
Yes.
strictly different.
I don't think it is. Because these are only the intersection points, this graph down here.
Oh, okay. Sorry.
Okay.
Wait, but like then there should be 2 in between like the other.
And yeah, that's how those are the edges I'm going to add in if my pen works. Which is not. Okay, I'll restart OneNote. Okay, how's that? Nice. Okay, cool. So you've got... Huh? So like you've got additional edges around here. And I think there's additional edge. That's that one. And then these ones have double-ended ones. Okay. And these all have... Hang on. Is this working? Is the stream broken?
No, it's fine.
Okay, cool. So basically we've got these. We might have some additional non-intersection points. So points like this, this, and this would all be these like additional nodes in here. But one of the problems that we run into if we just create this graph is that if we have, well, say we had like a good old cycle, and then we had 2 paths between nodes.
Hold on.
Yeah.
Isn't that graph like the exact same as the graph you did before, except just drawn differently?
Except it's just with the intersections.
Well,
Basically,
then you added the extra nodes in, right?
Well, they added the extra nodes in, but we're gonna really only care about the intersections.
Right.
Those
so
these were just
drew those in for clarity.
Yeah, they're just for clarity.
Okay, cool.
Okay, we'll just quickly talk them out. Okay, one of the problems that we run into is that when we go to these extra points, is that we don't know the orientation of this. Is the area of this section, is it going to be the area of this polygon, or is it going to be the area of this polygon? And so, like, the best example I found of this was here. Do we care about is the positive area going to be this one here, or is it going to because we've only been looking at intersections, is it going to take this one when it shouldn't? And so this was a slightly annoying problem that I that took a while for me to work out, which is that if we try and create an Euler tour of this graph is Euler
if we just create it.
Eulerian cycle.
Yep.
Yeah, same thing. Okay, so if we create this and we do it such that we try and like keep it as tight as possible, and this is including all these additional edges.
But you can
I
do an
think
Eulerian cycle.
the thing is, if we just do a regular Eulerian cycle, then basically what you have is you might go on these long paths, and going on a long path is not really what we want if we're trying to take advantage of the fact that adjacent regions are like go into different sort of categories.
Yep.
And so basically I said, so basically what if we try and keep our Eulerian cycle very, very tight? And so basically, what if we chose this one here, and we try and take basically a path that's like very, very tight. So it's going to come around here, and it's going to come directly back to this node. Okay, and now if we do the same thing, but from this node.
So you modify it.
So basically, you know that if you have an algorithm for an Euler tour, if you don't have an Euler tour, if you just take this path, then you can just augment it by this.
Yep. Well,
that doesn't quite work.
Have one.
Yeah. Okay, but
yeah.
But if you can come back, then that's good. So basically, we're going to try and keep our circuit as like tight as possible. And so I think if we do that, then we sort of get each additional time we are adding on like part of this graph that we can like attach to our thing. Attach.
Is this just for building the dual graph?
Yeah.
Right.
This is sort of how I imagined it.
Building dual graph seems a bit. Okay, I think I don't know.
I think it might have been overkill, but or maybe it breaks. Because I couldn't think of like an easy way to prove that this sort of works. I think it almost doesn't break.
Okay, so we just want to find faces we just want to find regions in the graph, right?
Yeah.
Okay, so a region in the graph is just Hold up.
I wonder if we just pick an arbitrary node and then find the find the circuit of the shortest path that comes of the shortest circuit, and then we denote that as one color. And then if we continuously expand on that, and then one way that we can test is so actually, and then basically if you could find those two areas, and then the way that you finally observe which color is which is if you just observe that all these outside ones are positive, because you can sort of think this entire thing is negative. If you think about it that way, then because of the problem statement that no 3 points are collinear, and actually I think something I forgot to add to the problem statement, which was that you also guarantee that there is an intersection between them. So like one doesn't completely lie inside the other. Like this just doesn't happen. And that combined with the fact that none of them are collinear is that there always exists one point that is completely outside the rectangle. And if you do the polygon interior, then you find that whatever sort of segment that is connected to, that is the positive segment.
Oh, by the way, if you just want an algorithm to output a dual graph, there's a pretty easy one. Is that what you want?
Wait, what's the dual graph?
If you just have a graph of like nodes such as that, and you want to output the dual graph of that graph.
Wait, would that account for like the orientation of?
Yes.
Okay, that accounts for the orientation of this versus like these two being swapped.
It just does it.
Okay, oh, it does
essentially, yeah, like given any planar graph, it constructs a dual.
Oh, nice.
As long as you know the points in space, but like it's CompGeom, so you do.
Okay, yeah.
So the way it works is you kind of start at a node, right? And you do like a right-handed walk around the for each node you order the edges clockwise from like an arbitrary starting position, right? And then like you do kind of like a right-handed walk where like each time you kind of like you're almost like walking a maze. You just kind of just hug the left wall, if you know what I mean.
Oh, okay, yeah.
And you just continue hugging, and then like once you've hugged that, you record all the edges, and that's like the edges in that kind of node in the dual graph. And then so once you've found all the edges, you kind of also record for each edge the dual graph nodes that touch that edge, and there's exactly 2 of them. So like essentially you've already built your graph like that. And I think with that actually solves your problem, because we can also find the outside with the same right-handed walk. We essentially find the leftmost point, right? And we know that like anything further to the left, the leftmost point must be outside. So we do a right-handed walk pointing directly backwards from the leftmost point, and then we can find the outside region. And then we can find like the regions inside, and then we can just build the planar graph like that. Build the dual of the planar graph like that. And then if we calculate for each polygon the area, which is doable in like linear time, then we'll be able to solve your problem. That's pretty AC.
That does sound like AC. Okay, so
like the intuition is the right-handed walk.
So like, because the original idea I had for this was that if you take something and basically the original idea for the problem was that if you have this and you would, whenever you get to an intersection, you would like switch onto the other polygon. But then I thought that if I did this, then there'd be no way to like find the orientation. But I suppose if you find some way to choose which way you're going, as in like going this way versus this way, then I suppose that right-handed walk sort of works. That does sound like AC. And how does this right-handed walk work? Let's see. Okay, I see. Oh, what? Oh, okay, you're on stream.
Yes, hello. I am on stream.
Wait, you on stream this entire time?
No, just a bit. I was just on stream for a bit. Essentially, I'm going to construct a planar graph, and I'm going to tell you how the right-hand walk works. I wonder if J-King is going to do the same thing.
Why is he?
Oh, Ryan just left. Rip.
Okay,
Right,
I
are you
wonder.
watching my stream now?
Yeah.
So we have this, right? We
Yep.
have this, right? Okay, so we just pick a node arbitrarily because we're going to visit all of them anyway. And let's suppose we're actually no, a state is actually the edge and the direction we're headed on that edge. So they're like this order number of edges states.
Yep.
Yeah. So let's suppose we're here, right? Let's use a different color. Let's go red. So we know that this is going to be part of our kind of walk, right?
Yep.
And then now we're here. And then we transition to here, this edge. And this is not like this is the hard part because like now we reach this node, we kind of have to figure out the next node we're going to. So considering it's a right-handed walk, we're going to walk on the we're trying to find this polygon here. So what we do is we first of all set a vector pointing directly backwards, right?
Yep.
And then we kind of just hit the next vector that